Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 13, Interpreting the Graph of a Function. Classwork. This graphic was shared by NASA prior to the Mars Curiosity rover landing on August 6, 2012. It depicts the landing sequence for the Curiosity rover's descent to the surface of the planet. Okay, so let's just go through all this real quickly. Sky crane details. So this is rover separation, touchdown, mobility, deploy. This is all happening down here. It's like a blown up. So let's start over here. Cruise stage separation, time of entry 10 minutes. Cruise balance devices separation, time entry, and then there's a squiggly line and an 8 min. And that little squiggly line, this, like this, 8, means approximately 8 minutes. Entry interface, altitude approximately 78 miles or 125 kilometers. The velocity was approximately 13,200 miles per hour. Time entry plus 0 seconds. And then peak heating. When something enters an atmosphere, there's resistance, and then there creates heat. Peak deceleration, and then hypersonic aero maneuvering. Heat shield separation. Once the heating process is over, the heat shield separated, and that was at an altitude of approximately 5 miles at a velocity of approximately 280 miles per hour, and time of entry at plus approximately 278 seconds. Or just shy of 5 minutes. 300 seconds is 5 minutes. Hypersonic aero maneuvering, parachute deployed at the altitude of approximately 7 miles with a velocity of 900 miles per hour. And the time entry then was plus approximately 254 seconds. 6 seconds shy of 3 minutes, or 5 minutes. 6 seconds shy of 5 minutes. And then it continues on. Radar data collection occurs, and back shell separation altitude occurred at approximately 1 mile. Velocity was approximately 180 miles per hour, and the time of entry at this point was plus approximately 364 seconds. Powered descent, sky crane, and fly away. So the sky crane details up here. Rover separation 66 feet. Velocity approximately 1.7 miles per hour. Time entry, it took approximately 400 seconds. And then the touchdown, altitude 0, velocity approximately 1.7 miles per hour when it landed, and the time entry was approximately 416 seconds. And then it flew away. So the question down here says, does this graphic really represent the landing path of the Curiosity rover? Did it really shoot over here and then curve and then slow down like this and then land? And it says create a model that can be used to predict the altitude and velocity of the Curiosity rover 5, 4, 3, 2, and 1 minutes before landing. Okay, so the information that's available in this graphic here is the altitude and velocity at various times. Various landing stages are named, and time 0 is at the point called entry interface. What information is in the box in the upper right corner? So this information here contains a detailed information about the final seconds of the landing sequence. Okay, so then there are negative time values. So the creators of this graphic are referencing time since entry interface began. The time associated with the stages before this stage would be negative. Velocities shown are all positive, but a calculation of average velocity using the altitude as the distance function shows that the velocities listed in the graphic really should be negative. So use negative values for velocities when necessary. In the graphic, what does the symbol squiggly line mean? Well, I already mentioned that. That was this right here. That means approximately. And which units, metric, or customary make this problem easier to understand? Okay, and that all depends on the individual. Some people prefer to use miles per hour because they can relate that to everyday life, because that's what we use in the United States. But if you're using meters instead, meters are always in tens, so they're much easier to calculate. Okay, on to page 2, mathematical modeling exercise. It says to create a model to help you answer the problem and estimate the altitude and velocity at various times during landing sequence. Okay, so I've created this table here and we're going to fill it in. So this is going to be times. And then we're going to altitude, and this is time in seconds. And the altitude we're going to use miles. And velocity. And velocity is miles per second. Okay, so here we go. So I'm going to have to go back and forth and back and forth. There's really no way for me to copy that entire page and fit it here and work around it. So I'm just going to keep arrowing back here. And so the time of entry would be 0 seconds. And the altitude is what? Okay, so when we're looking at the information here, it says time entry 10 minutes, time entry 8 minutes, cruise balance devices separation, entry interface. Then this is our first information that we have that gives us an altitude and a velocity. So the altitude is 78 miles, which is approximately 125 kilometers. So we're going to use the kilometers here and we're going to change it to meters. So 125 kilometers, a kilometer is 1,000 meters, so 125 kilometers is 125,000 meters. So I'm just going to write that for the first. So 125 kilometers is 125,000 meters. And our altitude, or our time is 0, right here, time entry 0 seconds. Okay, so that's going to be our entry is 0 seconds. 1,250 meters. So that goes here. And 125,000 meters at time 0. And the velocity is meters per second. So if I go back, the velocity in meters per second was 5,900 and it's negative 5,900. So negative 5,900 is the velocity. Then the next one that we look at is okay, so I had to look around at this. So notice that this says time entry 0 seconds, time entry 278, 254, 364. Well, we're not going backwards in time, so to get from 0 to 278, we have to get to 254 first. This is less. So the parachute deployed before the heat shield separated. Okay, so the order of this looks like it would go from here to here, but it doesn't. The parachute deployed first. So that is at altitude 11 kilometers. So that is our 11,000, or I'm sorry, 11,000 meters. So that's going to be 11,000 meters, and it's 254 seconds. So I'll put that first. 254 seconds, and it's 11,000 meters. And then go back and look at the velocity. And the velocity is negative 405 meters per second. Okay, so on to the next one. Now we're going to do, let's see, we just did 254 seconds. The next one is the heat shield separation, which is this one here. The kilometers are 8,000 meters. So 8,000 meters Seconds is 278. And velocity is negative 125. So velocity is negative 125, 8,000 meters, and the time was 278 seconds. The next interval we're going to look at is the back shield separation. Okay, the time is 364 seconds, and it's 1.6 kilometers, which is 1,600 meters. So 364 seconds and 1,600 meters. And then we go back, and the velocity at that time was 80 meters per second, negative. Okay, next one. Now we have to go into the last seconds, and that is in the sky crane detail. And 416, 400 is less. It's going to be the 400 first. So it's 400 seconds, 750 meters is the velocity, and the altitude is 20 meters. So the altitude is 20 meters. The velocity was negative 0.75, and the time was 400 seconds. Okay, let me just check my numbers. 400 seconds, 75 meters, and 20 meters. Okay. And then finally, the last one, wrong way. The last one is touchdown. So time entry is 416 seconds, 0.75 again, and altitude is 0. So 416 seconds, altitude 0, and the velocity is still 0.75. Okay, so if we were to graph this, make sure your graph has a heading, altitude meters versus time seconds. The x-axis would be our time in seconds, and altitude in meters is our y, or our dependent variable. So the altitude depends on how much time has elapsed. Altitude in meters is depicted by this gray line. So we started here at a little over 120,000, which is 125,000. It went down to 11, and it continued down, and then it slowed, and then we ended up landing. After a little more than 400 seconds, we are at 0. Okay, so what happened here was this thing was a constant decrease in elevation. It was coming into the atmosphere, where at this point right here where it slowed, that would have probably been where the parachute deployed, and then this is where the heat shields broke free, and then landing. Okay, so now here is a graph of velocity, meters per second versus time seconds. So this graph here is this times an altitude. Okay, so I color-coded everything to make it clearer. So our time seconds is our x or our t axis down here on both, 0 to 500 on both t axis. The blue altitude, m meters, is this blue line depicted here. Okay, and so it's decreasing as we're approaching land. Obviously, if you're landing, altitude is going down as time is increasing or time is going by. But in the velocity graph, as time passes, the velocity is decreasing, and it's decreasing from negative 5,900 all the way down to negative 0.75. So it doesn't ever get right to the 0 timeline axis. But as you can see, as time goes by, the velocity is getting closer and closer to 0. Okay, so that might be a little confusing to you, because if something is decreasing, then it negatively should be getting larger. But just think of it as decreasing is getting closer to 0, not so much as getting greater negative. So these are the two graphs that you would have gotten from altitude and velocity. Okay, on to page 3, exercises. 1. Does the graphic really represent the land path of the Curiosity rover? So if we look at this, does that really represent the path? So I'm questioning this here and also this right here. Okay, so the answer is right here, and the answer is no. The height is not scaled appropriately in this graphic. According to the video, it also looks as if the Curiosity rover rises a bit when the parachute is released and when the sky crane engages. Now, when it says the video, there are videos, animations, articles, all about this event, and I will have them connected to this video. They'll be in a link. So if you see the link below the video, you can click on those and watch those videos and animations as well. Okay, so number 2 says to estimate the altitude and velocity of the Curiosity rover 5, 4, 3, 2, and 1 minute before landing, and explain how you arrived at your estimate. So first of all, we are going to use the graph and we will use the graph and round the landing times to be at 7 minutes after entry interface. So the table here is going to show the altitude and velocity. So we're going to round. Okay, so some of these values are going to come from the video because they aren't here. But time since entry, so if time entry was at 10 minutes, it entered at 10 minutes. Cruise stage separation, okay, at 10 minutes. So time since entry, 8 minutes, would be 2 minutes. Time since entry would be 2 minutes right here. And so that's what we're going to start with. So if I go down here, then I'm going to enter time since entry. Interface is going to be 2 minutes. Altitude in miles was 45, and the velocity miles per hour was negative 7,500. Okay, and I'm just going to fill this in because it's a lot of going back and forth, and plus there's the video that I'm not going to play within this video. Those don't always work very well. But then the next time since interface will be 3 minutes. That would be at the 7-minute mark from entry, which would be at, it's not here, it is in the video, because if we enter and we're 3 minutes from entry, that's 180 seconds. And we don't get information in here until 278 seconds. So I'm just going to fill in this table with respect to the other information given. And it will be time since entry interface would be 3. The altitude at that time is 28 miles, and the velocity was 4,500. And this was supposed to be 7,500 up here. Okay. So number 4, or 4 minutes since entry, is altitude of 10 miles and a velocity of negative 1,500 miles per hour. Okay, so time since entry interface 5 minutes. So 5 minutes after it entered, the altitude was 4 miles, and that was negative 260. And then finally 6 would be 1 mile altitude and negative 180 miles. Velocity is negative 180 miles per hour. Okay, so there's our table for that information. Okay, so here is the graph, altitude with respect to time. And we started way up here at 0. So at time since entry, 2, we were at 45. So 2 is right here, 45. Let me get a pen so it points better. So 2 is right here at 45. 3, we were down to 28. 4, we were down to 10. 5, we were down to 4, and 6, we were down to 1. So that's this graphed. Okay, so the velocity with respect to time is graphed like this. So it's very similar to what we did before on the previous page. And as time goes by, our velocity is getting closer and closer to 0. Okay, page 4. Number 3. Based on watching the video, animation, do you think you need to revise any of your work? Explain why or why not, and then make any needed changes. So here it is. Obviously, answers will vary. Some students might suggest that the period of rapid descent and deceleration cannot be linear. Some may suggest that their graphs take into account the period of upward motion when the parachute is released and the sky crane engages. Number 4. Why is the graph of the altitude function decreasing and the graph of the velocity function increasing on its domain? Okay, so the answer to that is the altitude values are getting smaller as the time values increase, and the velocity values are getting larger as the time values are increasing. Number 5, why is the graph of the velocity function negative, and why does the graph not have a t-intercept? Okay, the graph is negative because we represent velocity as a negative quantity when the distance between two objects, in this case the Curiosity rover and the surface of Mars, is decreasing. The graph does not have a t-intercept because the Curiosity rover is traveling at negative 1.7 miles per hour when it touches the surface of the planet. And number 6 says, what is the meaning of the t-intercept of the altitude graph? And what is the y-intercept? Okay, the t-intercept is the time when the Curiosity rover lands on the surface of Mars. The y-intercept is the height of the Curiosity rover when entry interface begins. Okay, here's page 5. The Mars rover collected the following temperature data over 1.6 Martian days. A Martian day is called a sol. Use the graph to answer the following questions. The length of a sol varies as it does on Earth, with the mean time of one sol being 24 hours, 39 minutes, and 35 seconds. Ground and air temperature sensor. So this is temperature in degrees Celsius, and this is sols or Martian days. Ground temperature and air temperature, and this is graphing both. Okay, so it says, approximately when does each graph change from increasing to decreasing and from decreasing to increasing? Okay, so when a graph changes from increasing to decreasing, it's called a relative maximum. And for the air temperature, that's the darker line here, it went from increasing to decreasing right here. And what else is it asking? From decreasing to increasing. So it increased all the way this way, and it decreased from here down to here, but then it increased from here to here, and then it decreased from here to here, and then it increased from here all the way up to here, and then it decreased from here down to this lowest point right here, and then it increased from here up. Okay, so now if we look at the ground temperature, this is a relative minimum, so it increased from here all the way to approximately this point right here, and then it decreased from here all the way down to, I would say, about here. It did have a slight increase there, but then it decreased. And then it goes from decreasing here to increasing all the way up to the end. Okay, so here are the values. Increasing to decreasing air, approximately 10.18. So 10.18 would be about here, and 10.59 is probably right around here. It's right here, 10.59. And then ground, approximately 10.52. The ground temperature is the red, so that's 10.52, which is this point right here. Let me change color to green. This is my 10.4, 10.6, 10.5 here, 10.52, and 11.12. So this is increasing to decreasing. 11.12. So 11.2 is here, 11 is here, 11.12 would be right here. From increasing to decreasing. And then decreasing to increasing air is the blue line. Decreasing to increasing, 10.12, which is right about here. It's going from decreasing to increasing right here. And at 10.25, which is, let's see, 10.25 sol. Decreasing to increasing. Air. Air is this line. 10.25. Decreasing to increasing is right here. There's 10.25. So it went from decreasing to increasing at this point right here. And at 11.2, which is over here, 11.2, which I marked right here. 11.1 and 11.2 sol. And 10.2. So 10.2, 11.1, which is here. So it goes from decreasing to increasing there, and then decreasing to increasing here. So those are the 11.2 and 11.1s right here and here. So decreasing, increasing, decreasing to increasing, decreasing to increasing. Whew. Okay. When is the air temperature increasing? Let's get all these dots out of the way. So here's the air temperature. When is it increasing? Well, it increased here, and it increased here. And then it also increased from about here to here. Those are all points of increase. Okay, so here are the intervals. 10.12, which is right here, to 10.18. And then 10.25 is right here to 10.59, which is almost 11, or 10, almost 10.6 right here. And then 11.2, which is right here, to 11.5. Okay, page 6, problem number 9. Question number 9, I should say. When is the ground temperature decreasing? So I have to go back to my table, or my graph, and let me label it. Let me get rid of these lines here. So we're talking about ground temperature decreasing. So I'll use red for decreasing. Ground temperature is the red line. It is decreasing from here to here. It is decreasing from this highest point here, decreasing, 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 decreasing to there. It increased for a second, but then it decreased again to there, and then it increased. So there's 1, 2, 3 different intervals where it decreased. So it decreased from 10 to 10.2. It decreased from 10 point, what is that, 4.8 maybe, somewhere around there, down to 11.1 almost, and then maybe 11.1 something down to 11.2. So I will bring in the intervals. Okay, so ground temperature decreased on the interval from 10 to 10.2, 10.55 to 11.1, and about 11.14 to 11.2. What is the air temperature change on this time interval? How much did the temperature change is what they're saying. So to determine air temperature change, first of all, we're talking about air temperature, the darker line here. We want to know what the high is, which is right here, 28 degrees Fahrenheit. And we want to know what the low was. And the low is right here. That is lower than these two here, and that is negative 103 degrees Fahrenheit. Brr, that's cold. All right, so that's number 10. So here's the answer. The high is 28 Fahrenheit and the low is 103 degrees, negative 103 degrees Fahrenheit. That is a change of 131 Fahrenheit degrees. Students might also answer in Celsius units, but I did it in Fahrenheit. Number 11. Why do you think the ground temperature changed more than the air temperature? Is that typical on Earth? Okay, so why do you think? The word do you think, nobody thinks the same. Think is an assumption, okay, an opinion. What do you think the ground temperature changed more than, why do you think it changed more than the air temperature? There could be multiple reasons. Atmosphere, what the ground is made of, what does it consist of, what kind of elements make up the dirt or the soil or whatever you want to call it. And that is not typical on Earth. Usually the ground is a more consistent temperature, where temperature in the air can change more drastically than the ground. Number 12, is there a time when the air and ground were the same temperature? Okay, well that would be where our two lines would intersect, isn't it? So where was the ground and air temperature the same? Let me use something bright like red. All right, so they intersected right here. So at 10.3 sols, the air and the ground were both negative 60 degrees Celsius. And then right here, at just over 10.6 sols, the air and the ground temperature was around negative, I don't know, 10 degrees. And then again right here at 11.3 sols, they were both negative 60 degrees Celsius. The air and ground temperature are the same at the following times: 10.3, 10.62, and 11.3 sol. Better call Sol. Okay. All right. Okay, page 7. That is the end of lesson 13. Go to your problem set. Now this video, I will say at the end of this video, I will say that this was a difficult video to explain things. It's more of a science type lesson, and